Ancient furnaces did more than just create tools and treasures. They reshaped the very world around them. Long before smokestacks dotted the horizon, human ambition was already etching a permanent record of its presence into the planet itself. This is the story of ancient smelting, an operation we often picture as small and contained. But the truth reveals something far more powerful. It was an ecological force. Today, we will trace how the hunger for metal permanently altered local ecosystems on a scale that still echoes in our soil, our ice, and our forests. By the end, you will see human history through an entirely new lens, one where our environmental impact stretches back not centuries, but how did the smoke from a Roman furnace end up preserved in Arctic ice? What invisible scars did a Bronze Age foundry leave upon the land? The answers rewrite our understanding of progress itself. What does it mean to find our fingerprints on a world we thought was untouched? The furnace was an insatiable machine. To understand its true impact, we must first grasp the staggering scale of its appetite. Think of ancient smelting not as a craft, but as the heavy industry of its time. It was an operation of immense material and energy throughput, a relentless process that consumed landscapes to produce a concentrated, gleaming result. The basic principle was simple, yet its demands were colossal. To extract metal from rock, you need three things in enormous quantities: ore, fuel, and heat. Take copper, one of the first metals humanity mastered. The ore itself is often a green or azurite, beautiful but stubborn. Inside that rock, the copper is chemically bound, locked away. To free it, you must subject it to a transformative blast of heat within a specially built furnace, typically lined with clay. But raw heat is not enough. You need a chemical partner, a reducing agent. That is where the charcoal comes in. As the charcoal burns, it does more than produce flames. It releases carbon monoxide, a gas that literally steals the oxygen atoms away from the copper ore. This chemical robbery is the heart of smelting. It leaves behind a pool of molten metal and a worthless, stony waste called slag. Now, consider the numbers. To produce just 1 single kilogram of copper, an ancient smelter might need to process 100, 200, even 300 kilograms of raw ore. That is a small mountain of rock, mined, hauled, and crushed by hand, all for a lump of metal the size of a fist. But the ore is only part of the equation. The true ecological cost was measured in trees. To achieve and maintain the scorching temperatures needed for hours, that same 1 kilogram of copper could devour an astonishing amount of charcoal. We are talking about hundreds of kilograms of wood, transformed into charcoal just to fuel a single batch. This means for every gleaming copper ingot, entire groves of trees were harvested, cut, stacked into mounds, covered with earth, and slowly burned in a low-oxygen environment to create that perfect, carbon-rich fuel. The operation was a funnel, a vast input of forest and mountain feeding a tiny output of refined metal. A single furnace might seem small, but its supply chain was enormous. To keep it burning day after day, season after season, required a dedicated, relentless harvesting of the surrounding woodland. This was not a light touch on the environment. It was a sustained, systematic drawdown of natural capital. The local ecosystem became, quite literally, the feedstock for human ambition. So when we picture a Bronze Age foundry, we should not just see the fire and the artisans. We must see the empty hillsides, the charcoal burners' smoky pits in the forest, and the endless lines of people carrying baskets of ore. This scale is what transformed a local craft into a global force, one that began to rewrite the rules of the landscape itself. That relentless consumption left a permanent signature. While the furnaces themselves fell silent long ago, their environmental impact did not simply fade away. It was captured, sealed in nature's own archives, waiting for modern science to learn how to read it. The evidence for these ancient alterations is not found in history books, but in the Earth itself. Researchers now turn to silent witnesses, natural record keepers that have meticulously logged centuries of atmospheric fallout. These are called environmental proxies, and they provide a startlingly precise diary of human industry. Picture a remote peat bog, a thick, waterlogged sponge of decaying plant matter that grows slowly upward over. Each new layer traps dust, pollen, and microscopic particles from the air. Or consider the quiet depths of a lake bed, where a steady rain of sediment, including whatever metals are drifting in the wind, settles into neat, chronological stripes. Most strikingly, scientists look to the ice sheets of Greenland. Here, each year's snowfall compacts into ice, preserving bubbles of ancient atmosphere and capturing whatever contaminants were circling the globe. Within these pristine layers, researchers hunt for specific chemical fingerprints, particularly isotopes of lead and copper. These are variations of the metal atoms themselves, with slightly different weights. The ratio of these isotopes acts like a unique signature. Lead pollution from a Chinese bronze foundry has a different isotopic mix than lead from a Spanish silver mine. By extracting cores from these ice sheets, like reading the rings of a giant tree, scientists can pinpoint exact years. What they find is undeniable. The data reveals sharp, sustained spikes in atmospheric lead and copper pollution that align perfectly with the rise of major metallurgical powers. A dramatic increase appears during the height of the Roman Empire, whose vast plumbing systems and coinage demanded massive silver and lead smelting. Another pronounced spike coincides with the economic boom of China's Song dynasty over 1,000 years ago. These are not vague traces. They are clear, datable signals of industrial activity recorded in ice thousands of miles from any furnace. This is the hard data behind the claim of permanent alteration. The planet itself absorbed the byproducts of our ancient ambitions, filing them away in a global ledger. These proxies tell us that human activity began influencing atmospheric chemistry on a continental scale, not with the Industrial Revolution, but thousands of years earlier. The world we often call pristine was already bearing our invisible metallic mark. The Roman appetite for metal was a force of nature. To grasp its true scale, look to a place like in southwestern Spain. For centuries, this was not just a mine. It was a sprawling industrial complex, a landscape utterly transformed by the empire's hunger for silver and the lead that came with it. Roman operations, they were staggering in their ambition. They employed complex systems of aqueducts to bring water for washing ore and hydraulic mining, using the power of water itself to blast away hillsides. They dug networks of tunnels so extensive they formed underground cities of labor. The primary goal was silver, essential for coinage and luxury, but the process extracted a hidden cost: massive amounts of lead, a toxic byproduct released freely into the environment. The scale is almost unimaginable by ancient standards. Historians estimate that Roman lead production reached tens of thousands of tons per year. This was not cottage industry, this was systematic, continent-wide exploitation, and the planet recorded every ounce of it. Those Greenland ice cores tell a startling story. They show a dramatic spike in atmospheric lead pollution that begins with the rise of the Republic, peaks during the height of the Empire, and then falls sharply after its decline. This Roman peak was so profound that global lead pollution did not reach comparable levels again until the Industrial Revolution, over 1,500 years later. Think about that for a moment. The exhaust from Roman smelters, carried on the winds, settled into the ice of the Arctic, creating a pollution signature that would stand unmatched for more than a millennium. This is the undeniable data, a chemical echo of ancient industry written in the Earth's own frozen history. But the impact was intensely local too. To fuel those Spanish furnaces, forests fell. Every ton of lead and silver required many tons of charcoal, which meant the systematic clearing of woodlands for miles around. This deforestation likely triggered a cascade of secondary effects. Without tree roots to hold the soil, mining regions would have faced severe erosion. Hillsides stripped for timber, and by mining would have washed away with every rain, choking rivers with silt and altering local hydrology. The very shape of the land, its ability to absorb water and support life, was changed. So the Roman industrial footprint was twofold: a global atmospheric signature and a local ecological restructuring. Their legacy is not only in aqueducts and roads, but in altered soil profiles and silent layers of ice, a permanent reminder that even ancient industry could reshape a world. The story of metal's ecological footprint is not a uniquely Roman tale. Across the world, other civilizations were writing their own chapters in the same global ledger. In the fertile central plains of ancient China, during the Shang and Zhou dynasties, a different kind of metal was becoming the lifeblood of power and spirituality: bronze. The scale of their bronze production was nothing short of monumental. Think of the legendary ritual vessels, the massive cauldrons and intricate wine cups used to communicate with ancestors and affirm royal authority. These were not small trinkets. Some surviving vessels weigh hundreds of kilograms. To cast objects of this size and complexity required foundries of staggering capacity, with multiple furnaces roaring simultaneously, fed by armies of workers and fueled by an endless supply of charcoal. This was a state-sponsored industrial endeavor, central to the identity and stability of the dynasties themselves. But where did all the copper and tin come from? And what was the cost of turning that ore into sacred bronze? Modern science is now uncovering answers buried in the mud. Researchers have extracted sediment cores from ancient lakes situated near known Shang and Zhou mining and smelting regions. These muddy timelines tell a clear story. In layers dating precisely to the height of bronze production, the sediment shows a dramatic and sustained spike in metal particles, especially copper and lead. Alongside these metals, the cores are filled with microscopic charcoal dust, the atmospheric fallout from centuries of furnaces burning day and night. This is the direct environmental signature, the literal soot and metal rain from these ancient industrial sites. It proves the activity was not just a historical footnote, but a dominant feature of the local ecosystem. The ecological pressure this created was immense. Historical texts from the period occasionally lament a scarcity of timber, hinting at a changing landscape. The scientific evidence gives those hints profound weight. To produce the bronze for a single large ritual vessel might have consumed the wood from an entire acre of forest, processed into charcoal. Multiply that by thousands of vessels over centuries, and the demand becomes almost inconceivable. The hypothesis is compelling and sobering. The relentless need for furnace fuel likely drove systematic deforestation across the Central Plains. This loss of forest would have triggered a cascade of changes: increased soil erosion, altered local rainfall patterns, and reduced habitat. The very land that supported the agricultural surplus needed to feed the bronze workers may have been undermined by the industry itself. It presents a poignant duality. The same bronze that forged a cultural identity and connected kings to the heavens also reshaped the earth in ways those kings could never have imagined. The legacy of their spiritual craftsmanship is preserved not only in museums, but in the polluted mud of nearby lakes, a permanent record of an ecosystem forever changed by the pursuit of permanence. This relentless hunger for fuel created a silent crisis. While the gleaming metal was the goal, the true engine of every ancient smelting operation was the forest. Wood was the universal fuel, because it was the only widely available substance that could be transformed into a material capable of generating and sustaining the extreme heat required. But raw wood burns too quickly and unevenly for a furnace, so it had to be converted into charcoal first. This conversion process itself was a monument to inefficiency. To make charcoal, workers would carefully stack wood into large, dome-shaped mounds, cover it with earth or turf to limit oxygen, and then set it smoldering for days. The goal was to drive off water and volatile compounds, leaving behind a lightweight, carbon-rich fuel that burned hotter and longer. The catch: it took a staggering amount of wood. For every 10 units of wood you started with, you might end up with just 1 or 2 units of charcoal by weight. You were literally burning away most of the forest just to create the concentrated fuel to burn again in the furnace. This math created an unsustainable equation for any permanent settlement. A single smelting center, operating continuously, could consume the wood from several square miles of forest every year. Trees take decades, often centuries, to regrow to a usable size. The rate of harvesting for charcoal simply outraced nature's ability to recover. This led to what historians term a localized fuel crisis. The trees within a practical transport distance, maybe 10 or 15 miles, would be exhausted within a generation. When that happened, the entire operation faced a stark choice: relocate or collapse. We see this pattern etched across the archaeological record, with smelting sites abandoned not because the ore ran out, but because the fuel did. The community would have to pack up its knowledge and move on to a new, forested frontier, leaving a landscape behind. But the ecological impact of that deforestation did not end when the last furnace cooled. The cascading effects were profound and permanent. Without a dense network of roots to anchor the soil, the land became vulnerable. Rainfall, once absorbed by leaf litter and root systems, now ran off the bare hillsides, carrying away the precious topsoil in destructive floods. This erosion permanently changed the soil composition, stripping away nutrients and leaving behind a thinner, less fertile earth. The loss of tree canopy also altered the local microclimate, making temperatures more extreme and potentially reducing the moisture in the air. Habitats for countless species vanished, reducing biodiversity. The vegetative cover might eventually return as scrub or grassland, but the rich, complex old-growth forest was gone for good. The land itself had been fundamentally rebooted into a different, simpler state. So the pursuit of metal did not just pollute the air, it the ground beneath their feet, turning lush woodland into eroded slopes, all for the carbon needed to turn stone into power. Beyond the vanished forests lies a more intimate and enduring scar. While deforestation reshaped the landscape, the smelting process left behind a toxic inheritance buried in the very soil itself. This is a second, more direct mechanism of permanent change: heavy metal contamination. The ancient furnace was not a clean machine. It was a messy, inefficient chemical reactor. Alongside the desired metal, it released a cocktail of other elements locked within the ore. Lead, arsenic, copper, and zinc, these are the persistent byproducts of smelting, elements that do not break down, disappear, or wash entirely away. They are, for all practical purposes, permanent. Imagine the scene around an active smelting site. Furnaces belched not just heat, but fine metallic dust, a microscopic powder laden with toxins. This dust was carried on the wind, settling over everything downwind, coating leaves, fields, and waterways. Then there were the slag heaps, the massive piles of stony waste discarded after each smelt. To the untrained eye, they look like harmless hills, but rain falling on these piles acts like a slow chemical pump. Water percolates through the crushed rock, leaching out soluble metals and creating a toxic runoff that seeps into the surrounding earth and groundwater. Over decades and centuries, this process created vast, invisible zones of contamination radiating out from the industrial heart. The soil itself became a reservoir for poison. Modern environmental studies at ancient smelting sites from Britain to Bolivia confirm this lasting legacy. Scientists take core samples and find that soils just a short distance from ancient furnaces still contain levels of lead, arsenic, and copper that are hundreds, sometimes thousands of times higher than natural background levels. These concentrations are not relics, they are active. They continue to inhibit plant growth, stunting roots and preventing certain species from taking hold, which subtly alters the local ecology even today. More hauntingly, this soil contamination would have directly entered the ancient food chain. Grazing animals would have ingested contaminated plants and soil. Crops grown in these enriched fields would have absorbed the metals, passing them on to the people who tended them. While the full health implications for ancient communities are difficult to measure, the presence of these toxins in their environment and diet is an undeniable fact written in the dirt. So the legacy of ancient smelting is twofold: a visible reshaping of the hills and forests, and an invisible chemical alteration of the ground beneath our feet. The soil remembers what history often forgets, holding the metallic signature of ambitions that burned brightly and left a mark that time itself cannot erase. The air itself became a corrosive agent. While heavy metals settled into the soil, another invisible byproduct of smelting may have drifted into the clouds: sulfur dioxide. This gas is released in significant amounts when sulfide ores, common sources for copper, lead, and silver, are roasted and smelted. In the atmosphere, sulfur dioxide can transform into tiny droplets of sulfuric acid, which then fall back to Earth as acid rain. This is a process we strongly associate with modern coal-fired power plants, but its roots may reach deep into antiquity. The question is not whether ancient smelters produced the chemical ingredients for acid rain. They certainly did. The question is whether they produced enough, concentrated in one area for long enough, to meaningfully alter the local environment. The evidence suggests a compelling, localized yes. Consider a major smelting center operating for centuries, like the copper-producing regions of Cyprus or the silver mines of Ancient in Greece. These were not occasional workshops, they were industrial hubs where dozens of furnaces might burn simultaneously, year after year. The cumulative plume of sulfur dioxide from such a place would have been substantial. Prevailing winds would have carried this acidic cloud downwind, where it would have returned to Earth in rainfall. The impact would have been a quiet, chemical weathering of the landscape. Soil chemistry studies near ancient smelting sites often reveal unnaturally acidic soil layers corresponding to periods of peak production. This acidity is a lasting fingerprint. It alters the very chemistry of the earth, leaching away nutrients like calcium and potassium that plants need to thrive, while simultaneously making toxic metals like aluminum more soluble and dangerous to root systems. The consequences for the downwind ecosystem would have been a slow, strangling change. Coniferous forests, in particular, are vulnerable to soil acidification. The needles of pine or fir trees might have shown damage, turning brown and dropping prematurely. Growth would have slowed, leaving trees stunted and more susceptible to disease or harsh winters. Over time, the composition of the forest could have shifted entirely, with acid-tolerant species moving in as others died back. The damage would have extended to water systems as well. Acidic runoff flowing into streams and ponds could have lowered the pH of the water, creating an environment hostile to many forms of aquatic life. Fish eggs might have failed to hatch, and delicate insects that form the base of the food web could have disappeared, leaving the waterways quieter and less vibrant. This paints a more complete and more devastating picture of the ancient smelter's footprint. It was not merely a consumer of trees. It was an agent that could poison the land's fertility and the water's vitality from the air itself. The effect was undoubtedly localized, perhaps felt most severely within a few miles of the smelting center, but it adds a profound layer to the ecological disturbance. The community living and working there would have been surrounded by a triad of change, denuded hills from fuel gathering, metal-laced soil, and now, forests and streams subtly sickened by an acidic rain they could not see. It reveals an ancient industry that did not just extract from the environment, but actively changed its fundamental chemistry, leaving a legacy written in the acidity of the soil long after the last fire went out. The environment pushed back with a powerful, invisible hand. This was not a one-way street where industry simply consumed the landscape. The ecological changes caused by smelting, in a profound twist, began to shape the very societies that created them. This created a complex social feedback loop, where human ambition altered the environment, and that altered environment then redirected the course of human history. The most immediate pressure was the fuel crisis. As we have seen, a permanent smelting center could strip its local woodlands bare within a generation. When the trees were gone, the entire economic engine seized up. You cannot smelt metal without charcoal, and you cannot make charcoal without wood. This simple equation forced monumental decisions. Archaeological records from sites across Europe and Asia show a clear pattern: smelting centers often relocated not when the ore was exhausted, but when the fuel was. This meant uprooting communities of specialized workers, abandoning expensive infrastructure like furnaces and workshops, and seeking out new frontiers of forest. The very geography of metal production was dictated by the growth rate of trees, not just the location of veins of ore. This scarcity also reshaped economies and power dynamics. Regions rich in timber but poor in metal ore suddenly gained immense strategic value. Long-distance trade networks emerged not just for finished ingots, but for the fuel itself. There is evidence, for instance, that the ancient copper industries of Cyprus may have relied on timber imported by ship from the mainland. Control over a forest could become as important as control over a mine, creating new alliances, conflicts, and dependencies. The cost of metal would have inevitably risen as fuel had to be hauled from farther and farther away, making it a luxury and concentrating power in the hands of those who could afford the logistical burden. In some cases, this environmental pressure may have contributed to the decline or even collapse of local metalworking traditions. A society that built its wealth and military power on bronze weaponry would face a crisis if it could no longer produce that bronze. They might be forced to trade for it at disadvantageous rates or shift to less effective materials, making them vulnerable. Some researchers point to the mysterious decline of the Minoan civilization on Crete, speculating that the deforestation required to fuel their renowned bronze workshops may have led to soil erosion and agricultural decline, weakening the society from within. While never the sole cause, the ecological strain was a constant, slow pressure on the system. So the story comes full circle. The drive for metal changed the forests and the soil. Those changes then constrained future production, redirected trade routes, and influenced the rise and fall of industrial centers. It reveals a civilization in a delicate dance with its own environment, not as a master over nature, but as a powerful participant in a system that always, inevitably, responded. The choices made by a Bronze Age king or a Roman engineer were not made in a vacuum. They were made within an ecosystem they were actively reshaping, an ecosystem that, in turn, reshaped them. The most startling evidence of all is written not in soil, but in ice. Those ancient plumes of metallic dust did not simply settle near the furnaces, they embarked on a global journey. Carried by high-altitude winds, the invisible exhaust from Roman and Chinese smelters traveled thousands of miles, eventually falling as a fine, toxic snow upon the pristine glaciers of Greenland. There, layer by frozen layer, the planet preserved a precise chemical record of our industrial past. The data extracted from these deep ice cores delivers a humbling truth. Ancient smelting altered the very atmosphere of the entire northern hemisphere. The signature is lead. By measuring the concentration of lead particles in each annual layer of ice, scientists can construct a timeline of atmospheric pollution stretching back over 2,000 years. The graph they produce is not a gentle, natural baseline. It is a series of dramatic spikes that mirror the rise and fall of human empires. The most pronounced peak coincides precisely with the height of the Roman Empire. For centuries, lead from massive silver mining operations in places like Spain and Britain filled the air, was swept north, and settled onto the ice sheet. This Roman pollution peak was so immense that global lead levels did not reach such heights again until the widespread use of leaded gasoline in the 20th century. Think about the scale that implies. The exhaust from Roman furnaces created a hemispheric pollution event that stood unmatched for over 1,500 years. But the story does not end with Rome's fall. The ice cores record another, later surge during the medieval period, particularly between the years 1100 and 1300. This corresponds to a boom in silver mining across Europe, from the mountains of Germany to the peaks of the Alps, driven by economic expansion and a hunger for coinage. Once again, the byproducts of human ambition crossed continents and oceans, leaving a metallic fingerprint in a place no human had ever lived. This transforms our understanding of local impact. A furnace in Spain or a mine in Germany was not just reshaping its immediate surroundings. It was contributing to a diffuse, atmospheric change that affected the entire planet's chemical makeup. The lead that stunted tree growth downwind from a smelter was the same lead that drifted over the Arctic. The local ecosystem alteration we have been tracing, the deforestation, the soil poisoning, was merely the grounded, visible part of a much larger atmospheric process. It proves that even with ancient technology, human industry achieved a truly global reach. Our environmental footprint began not with the steam engine, but with the charcoal furnace. The ice holds the proof, a silent, frozen testament to the fact that the air we all share has carried the enduring echo of metal being born. The story of metal is the most dramatic, but it is not unique. The same fundamental equation, a hunger for transformative heat, drove other ancient industries that also reshaped their surroundings. To fully grasp the scale of our ancestors' environmental footprint, we must look beyond the furnace to the kiln and the salt pan. These were the other engines of the ancient world, powered by the same relentless consumption of wood. Take the production of pottery on an industrial scale. We often picture a single potter at a wheel, but for supplying cities, armies, or trade networks, Pottery was mass-produced in enormous updraft kilns. These structures could be large enough to walk into, stacked high with hundreds of vessels at a time. Firing a single load in such a kiln to the temperatures needed for durable, waterproof ceramics required a bonfire's worth of fuel, burned continuously for days. A major pottery center, producing for export, would have needed its own dedicated wood supply, leading to localized deforestation around clay pits and workshop districts. The demand was not as intense per unit as smelting, but it was constant and widespread, a steady pressure on woodlands wherever concentrated settlement arose. Even more fuel-intensive was the ancient production of salt, a vital commodity for preserving food. In regions without salt mines or solar evaporation ponds, people used a technique called. They would boil brine from salt springs or seawater in large, clay pans over open fires. To crystallize just 1 kilogram of salt from weak brine could require evaporating hundreds of liters of water, a process demanding an astonishing and continuous heat source. Archaeological sites from prehistoric coastal Europe show vast landscapes dedicated to this industry. With mounds of fired clay fragments from broken pans and thick layers of ash testifying to centuries of stop burning. The woodlands around these salt works would have been systematically harvested, creating open, managed zones of coppice trees or, eventually, cleared land. So what does this broader view reveal? It shows that metallurgy was the peak, the most resource-hungry expression of a pre-industrial pattern. The smelter demanded the most fuel per unit of output, released the most concentrated pollution, and left the most toxic legacy. But the potter and the salt maker were following the same logic, just on a slightly gentler slope. They were all participants in an ancient system of resource-intensive production. Their collective need for heat created a diffuse but significant draw on the environment, a pattern of localized fuel crises and landscape change repeated across continents. This context makes the story of ancient smelting even more powerful. It was not an aberration, but the most extreme example of a fundamental truth, that human civilization, even in its ancient forms, was built on a foundation of transformed energy and altered ecosystems. The quest for a ceramic jar, a cake of salt, or a bronze sword all shared a common cost, measured in the silent fall of trees and the slow change of the land. This evidence dismantles a comforting myth. We often romanticize the distant past, imagining our ancestors as living in a state of perfect ecological balance, the noble savage in tune with an untouched world. The story of ancient smelting shatters that illusion. It reveals a far more complex and human truth, that for thousands of years, societies have possessed a profound, if unintentional, capacity to reshape their environments on a permanent scale. The line between a natural landscape and a human-influenced one is not a product of the modern age. It is ancient, blurred by the smoke of Bronze Age furnaces and Roman smelters. These were not acts of malice, but of necessity and ambition. No Bronze Age metalworker lighting his furnace thought he was altering the chemistry of Arctic ice. He was solving an immediate problem, creating a tool, a weapon, a sacred object. Yet the collective outcome of countless such individual acts over centuries was a form of slow, planetary engineering. The ecological changes we have traced, from deforested hills in Spain to lead-polluted ice in Greenland, were not accidents. They were the inevitable physical consequences of a technological system operating at scale. This forces us to reconsider what we mean by natural. Is a forest that has on soil still laced with 3,000-year-old copper slag truly wild? Is a lake whose mud holds a permanent spike in charcoal dust from Zhou Dynasty foundries an untouched ecosystem. The evidence suggests these places are palimpsests, layered landscapes where human history is woven directly into the geology and chemistry of the site. They are neither purely natural nor purely artificial, but something in between, a testament to a long and continuous interaction. This does not diminish the scale of modern industrial impact, which is undeniably faster and more global. Instead, it provides crucial context. It shows that our current environmental challenges are not a sudden fall from grace, but an acceleration of a very old pattern. Understanding this deep history is not about assigning blame to the past, but about gaining clarity for our future. It removes the fantasy of a lost Eden and replaces it with a more sobering, and perhaps more useful, reality. We have always been agents of change in the world around us. The question left by the ancient smelters is not whether we alter our environment, but whether we can learn to foresee the consequences of that alteration and choose a different, more sustainable path forward. There is a profound irony in this ancient legacy of change. The very societies that transformed their landscapes on such a scale likely understood only the smallest fraction of the consequences they had set in motion. They were masters of the immediate cause and effect, the heat of the furnace and the flow of molten metal, but not of the invisible, far-reaching chain reactions they initiated. A Roman engineer would have keenly felt the pinch of a local fuel shortage, watching as the nearby forests grew thin and the cost of hauling wood from farther afield cut into profits. He might have even noted the poor health of crops downwind or the strange stillness in a nearby stream. What he could not possibly comprehend was that the lead dust from his operation was traveling on atmospheric currents to a frozen continent he did not know existed, leaving a permanent record in ice. The knowledge of the day was powerful but bounded by the horizon, by what could be seen, touched, and experienced directly. The concept of a globally interconnected biosphere, where actions in one hemisphere could subtly alter the chemistry of another, was thousands of years of scientific understanding away. So they operated in a kind of brilliant, dangerous blindness, solving the urgent problems of production while setting in motion slow-moving environmental changes that would outlast their empires. This disconnect between action and ultimate consequence is only half of the historical irony. The other half lies in the fragility of the knowledge itself. The sophisticated techniques of ore selection, furnace construction, and temperature control, the very knowledge that enabled this ecological transformation, was not stored in textbooks or databases. It was held in the hands and minds of generations of artisans, passed down through apprenticeship and lived experience. When a civilization faced upheaval, whether through conflict, economic collapse, or migration, these intricate webs of practical knowledge could fray and snap. The great smelting centers of the Bronze Age Mediterranean, for instance, fell silent for centuries after the widespread disruptions around 1200 BCE, the specific recipes for alloying bronze. The designs for the most efficient furnaces, the lore of which local ores yielded the best metal, much of this was fragmented or lost entirely in many regions. Societies that followed often had to relearn these arts from a much simpler starting point, a technological reset, so we are left with a haunting asymmetry. The environmental impact of their industry, the lead in the soil, the altered layers of lake sediment, the isotopic signature in the ice, these proved to be permanent. Locked into the physical world with a stubborn persistence. But the human understanding of how that impact was created, the sophisticated craft that caused it, was transient and vulnerable. The pollution became a silent, enduring testament, while the detailed knowledge of its origins faded into history. This is the layered legacy we uncover today. We use advanced geochemistry to read the environmental record they inadvertently wrote, piecing together a story of global reach that they themselves could never have told. It places us in a unique position of hindsight, looking back at the unintended footprints of ambition. It invites a sobering reflection. What are the slow-moving, invisible consequences of our own indispensable technologies? And what knowledge might we, in turn, one day forget, leaving only the physical evidence of our choices for some future civilization to puzzle over? Uncovering these invisible scars requires a new kind of archaeology. The story is no longer told by grand monuments or treasure-filled tombs, but by the silent chemistry of dirt and the ghostly outlines of vanished forests. To see what the ancient smelters truly left behind, scientists have assembled a toolkit of astonishing technologies, each one allowing us to peer deeper into a past we once thought was lost. This is a global detective story, and the clues are microscopic. One of the most powerful tools is geochemical soil analysis. Researchers take core samples from the ground near an ancient site, not to find artifacts, but to read the soil itself. Using sensitive instruments, they can detect parts per million of metals like lead, copper, or arsenic. They are not looking for chunks of ore, but for the faint, pervasive dust that settled from centuries of furnace smoke. By mapping the concentration of these elements, they can literally draw a pollution plume on a map, showing how the toxic fallout spread with the wind, defining the smelter's true zone of influence. It makes the invisible visible, revealing a contaminated landscape that has been hiding in plain sight for. Another revolutionary technology sees through the trees to find the past. LiDAR, which stands for light detection and ranging, uses laser pulses shot from an aircraft to map the ground surface with incredible precision. When flown over a forested region, these lasers penetrate the canopy to record the shape of the earth beneath. In places like the mountainous regions of Europe, LiDAR has revealed the staggering scale of ancient mining that was completely obscured by modern woodland. It shows not just a few holes, but entire mountainsides carved into terraces, vast networks of water channels for hydraulic mining, and the subtle depressions of thousands of prospecting pits. These are landscapes industrially altered on a massive scale, then reclaimed by nature, their true extent only now coming to light from the air. To understand what was lost, scientists turned to palynology, the study of ancient pollen. Pollen grains are incredibly tough, and different plants produce distinct shapes under a microscope. By extracting long cores from peat bogs or lake beds near an ancient industrial site, researchers can count these pollen grains layer by layer. The story they tell is dramatic. In layers dating to the peak of smelting, the pollen from large, old-growth trees like oak and pine often plummets. In its place, a spike appears in pollen from pioneer plants, weeds and grasses that thrive in disturbed, open ground. This is the direct botanical evidence of deforestation, a silent witness to the clearing of the woods for charcoal. Later, as the industry declines, the tree pollen may slowly return, but often it is a different mix, showing a permanently altered forest. Together, these techniques build an undeniable case. The geochemistry gives us the poison, the LiDAR shows us the industrial scars, and the pollen tells us what was erased. It is a form of time travel powered by particle accelerators, lasers, and microscopes. This modern toolkit does not just confirm historical records, it often writes the first draft of an environmental history that was never written down. It allows us to walk into a peaceful, green valley today and understand that we are standing in an ancient sacrifice zone, a place forever changed by the distant echo of fire and ambition. These changes force us to ask a difficult question. When we say an ecosystem was permanently altered, what does that word truly mean? The evidence is clear that ancient smelting left a mark, but not all marks are created equal. To understand the real legacy, we must differentiate between what is persistent and what is genuinely permanent. This is a distinction about time, scale, and the fundamental resilience of the natural world. Some alterations are so deep that they reset the baseline, creating a new normal that lasts for thousands of years, far beyond any human timescale we can easily comprehend. Other changes are profound and long-lasting, but nature, given enough centuries, can slowly begin to erase them. Recognizing this difference adds a crucial layer of nuance to the story. The most permanent scars are chemical. Heavy metal contamination in soil is the prime example of a truly irreversible change. When lead, arsenic, or copper from ancient smelting settled into the earth, it did not simply sit on the surface. Over centuries, these elements slowly migrated downward, binding tightly to soil particles. They do not degrade, they do not evaporate, and they are only removed by the unimaginably slow process of geological erosion. A soil profile showing a concentrated band of lead 2,000 years old is not a historical artifact. It is an active part of the present-day landscape. The metals are still there, still capable of being absorbed by plants or leached into groundwater. Even if the forest regrows, it is a forest rooted in poisoned ground. This kind of alteration creates a new, enduring chemical signature for that specific location. It is a permanent rewrite of the local geology, an anthropogenic layer as real as any volcanic deposit. The change is locked in, a testament that will last as long as the land itself. Species loss in a localized area can represent another form of permanent change. When ancient smelting led to complete deforestation and soil erosion, it may have created conditions that drove certain plants or animals from that specific valley or hillside forever. Even if a forest eventually returns, the complex web of life that existed in the old-growth ecosystem, with its specific mix of mosses, insects, fungi, and birds, is gone. What returns is often a simpler, different community. A particular species of orchid that thrived in the deep shade of ancient oaks, or a beetle that depended on a specific type of decaying wood, might find no pathway back. Their local extinction is permanent. The ecosystem has crossed a threshold, moving into a new, stable state that does not include them. This is a silent, biological form of permanence, where the footprint of industry is not metal in the soil, but an absence in the canopy. In contrast, some of the most visible changes were persistent, but not necessarily eternal. The of forests for charcoal is a powerful example. The loss of those trees was devastating and could last for many human generations, reshaping local climate, water cycles, and human society. But given enough time, and if the pressure is removed, trees can return. Seeds blow in from neighboring areas, and succession begins. It might take 200, 500, even 1,000 years for a complex, mature forest to re-establish itself, but the potential for recovery exists. The process is achingly slow by our standards, but it is a process. The scar is persistent, visible for centuries, but it is not a fundamental reprogramming of the soil chemistry in the same way. The land retains the memory of how to be a forest. This distinction matters because it shows that nature possesses an immense, if slow, capacity for healing from some wounds, but not from others. The ancient smelters inflicted both kinds, dealing blows from which some systems could eventually recover, while imposing other changes that became a permanent part of the land's very constitution. This framework helps us read the modern landscape with clearer eyes. A rolling, green hill in Cornwall or the mountains may look pristine and natural. But beneath that vibrant grass, the soil might still hold the lead signature of Roman or medieval mining. The forest that stands there today is a resilient regrowth, a testament to nature's persistence, but it grows atop a truly permanent human-made alteration. One story is written in the living trees, the other in the static chemistry of the dirt below. Both are true. This layered reality is the ultimate legacy of ancient industry, a combination of wounds that healed into scars and wounds that became part of the body itself. It challenges a simple narrative of destruction and instead reveals a complex dialogue between human activity and environmental change, where some consequences echo for, while others slowly fade into the green. That layered reality raises a profound question about our own place in the story. We rightly see the Industrial Revolution as a turning point in human history, a moment when our capacity to alter the planet exploded with the power of coal and steam. Its impact was, and remains, of a vastly greater magnitude and speed. The dense, choking smog over 19th-century London, the acid rain that devastated European forests in the 20th century, the sheer scale of global carbon emissions. These are phenomena on a different order entirely. To compare them directly to the output of a Roman furnace would be to miss the point. But the ancient evidence we have been exploring reveals something just as crucial. It shows that the fundamental patterns of our relationship with the environment, the very template of industrial impact, were established not 200, but 2,000 years ago. The difference is overwhelmingly one of degree, not kind. Ancient smelters were not proto-factories, but they were the first to enact a sequence we now know all too well, the concentrated consumption of a resource, localized deforestation. The release of persistent chemical pollutants and the creation of long-term toxic waste. They initiated the same feedback loops, where environmental change constrained future production and forced societal adaptation. They even achieved, on a modest but measurable scale, the same hemispheric dispersion of pollution. This is not to minimize the unprecedented challenges of the modern era, but to properly contextualize them. It establishes a deep, continuous history of anthropogenic, or human-caused, environmental change. The Industrial Revolution did not invent the concept of ecological disruption. It supercharged a process that was already ancient. This perspective is vital. It removes the idea that our current situation is a sudden, anomalous break from a harmonious past. Instead, it frames our modern environmental challenges as the latest, most intense chapter in a very long story. We are not the first civilization to reshape the world with our technology and face the consequences. We are simply the first to do it with the power to see the entire planetary system in real time. And to understand the full, global chain of cause and effect that our ancestors could only glimpse in their local valleys. The legacy of the ancient smelters is therefore a mirror. It shows us where we came from, revealing the enduring human drive to transform nature for our needs. But more importantly, it hands us a responsibility they never had, the knowledge of what that transformation truly costs, and the chance to write a different ending to this very old story. Yet for all we have uncovered, the full story remains frustratingly incomplete. The environmental record is like a book with crucial pages torn out. We can measure the lead in the soil and count the missing tree pollen, but we struggle to picture the living world that was lost. What was the true biodiversity cost in a smelting region? Our pollen cores tell us which trees vanished, but they are less precise about the understory plants, the insects, the birds, and the mammals that depended on that specific, complex habitat. The disappearance of a single keystone species, perhaps a particular type of woodpecker or a pollinating bee, could have triggered a cascade of other losses we can no longer trace. Reconstructing that lost web of life is one of the great challenges in this field. It requires piecing together scattered clues from animal bones found in archaeological sites, from ancient seeds preserved in unusual conditions, and from computer models that simulate how ecosystems collapse. Each new discovery adds a brushstroke, but the full portrait of what those pre-industrial forests and valleys actually contained may forever elude us. Another persistent mystery hangs in the ancient air itself. We have strong evidence for localized deforestation, but can we accurately model its microclimatic effects? Removing a vast swath of forest does more than just clear land. It changes how sunlight hits the ground, how moisture evaporates from leaves, and how wind moves across the terrain. Did the clearing of woodlands for Roman or Chinese furnaces create measurably warmer, drier, or windier conditions in those immediate valleys? Could it have even influenced very local rainfall patterns? Sophisticated climate models are now being applied to archaeological data, attempting to answer these questions. Researchers input maps of ancient land use based on pollen and settlement evidence into simulations to see if the ecological changes we know occurred might have also shifted the weather that people and their crops experienced. The answers could reveal a double burden for these communities, coping not only with resource scarcity, but with a subtly altered climate of their own making. Perhaps the most elusive question of all is cultural. How did these societies perceive the transformation unfolding around them? Did a Bronze Age metalworker, walking through hillsides now studded with stumps, feel a sense of loss or merely see progress? Was the erosion of soil into a once clear river viewed as a problem, or just an accepted fact of life? Ancient texts rarely comment directly on environmental change in a way we would recognize today. Their concerns were practical, immediate. A hymn might praise a fertile grove, a law code might punish the unauthorized cutting of a specific tree, but a philosophical treatise on landscape alteration is not something we possess. Some researchers look for indirect clues in mythology and art. Stories of wastelands, of curses that blight the land, or of gods angered by the smoke of forges, might encode a deep-seated cultural awareness of ecological damage. The evidence is subtle and open to interpretation, making this a frontier of historical imagination as much as hard science. This is why the research is so vibrantly alive today. Across the globe, interdisciplinary teams are pushing the boundaries. In Central Europe, scientists are using ancient DNA extracted from lake sediments to identify not just which plants were present, but the genetic diversity of those plant communities before and after industrial periods. In the Americas, projects are examining soil profiles around pre-Columbian metalworking sites to compare the ecological footprint of different technological traditions. And historians are meticulously rereading classical texts, legal documents, and even poetry, searching for new fragments of environmental perception. Each project acknowledges that our understanding is a work in progress. The legacy of ancient industry is not a closed case file, but an ongoing excavation, one that challenges us to listen more carefully to the silent testimony of the land, and to humbly accept that some echoes from the past may never fully come into focus. The evidence now forms a clear and startling picture. Ancient smelting was not a footnote in environmental history, it was a foundational force. The landscapes we often call pristine, from the rolling hills of Europe to the quiet forests of Asia, bear an invisible signature of human ambition, written in ice, soil, and sediment. This deep-time perspective fundamentally rewrites our timeline. Our environmental impact does not begin with smokestacks or plastic, but with the charcoal smoke of a Bronze Age furnace, with the lead dust that drifted from a Roman mine to settle in Arctic ice. The planet has been absorbing the byproducts of our progress creating a layered world where nature and human history are inseparably fused. This realization changes how we see both the past and the present. It means our contemporary environmental challenges are not a sudden fall from grace, but an acceleration of a very old relationship. Understanding that this dynamic stretches back thousands of years removes the fantasy of a lost Eden and replaces it with a more sobering truth. We have always been powerful agents of change. The question left by the ancient smelters is not whether we alter our world, but whether we can learn to see the full consequences of that alteration in time. Their legacy, locked in the earth, is a permanent reminder that our choices echo far beyond our own horizon. What other ancient mysteries of human-environment interaction do you think are waiting to be uncovered? Share your thoughts in the comments below.